In the previous lectures, we have learned about the basic concepts of the shear force and bending moment. We have learned how we are going to calculate the shear force at different sections of the beam, plus the bending moment at the different sections of the beam. And we have learned about the sign conventions which we had to use while we are calculating the shear force and bending moment at different sections of the beam. And finally, we learned how to construct a shear force diagram and a bending moment diagram. We have seen certain basic questions in the previous lectures. Now we are going to solve a few more problems with respect to the concepts which you have learned in the previous classes. So one example is shown here on the screen. There is a overhanging beam. Okay, it is an overhanging beam because the beam is supported between the ends, between the points A and B. We can see that there is a hinge at A and a roller support at B. This portion BC of the beam is the overhanging portion. Now, since we have a hinge support here, therefore we will have two reactions. One reaction will be in the vertical direction and another reaction will be in the horizontal direction. But since we aren't having any horizontal load acting on the beam, okay, we usually define the beam as the structural member which is subjected to the transverse loads. Okay, therefore we aren't having any kind of horizontal load, therefore there won't be any horizontal reaction in this case. Plus we have a roller support at B, therefore there will be a vertical reaction at B. Okay, so we also know that for the equilibrium of the beam, the summation of the forces in the vertical direction should be 0. Now the forces in the vertical direction are AY and BY are upward, and their summation has to be equal to the net force which is acting in the vertically downward direction. So we can see that there is a point load of 20 kilonewton, and there is a uniformly distributed load whose intensity is equal to 40 kilonewton per meter, and it is acting over a length of 80 meters. Therefore, if we want to calculate the total load on the account of this UDL, this will be given by the area under the loading diagram. Okay, that is equal to 40 into 8. So this will be 320 plus 20, that is, this will be equal to 340 kilonewtons. Also, the summation of the moments about any point should be 0. Let's calculate the moments about the hinge. So this gives us that the moment due to this vertical reaction about the point A will be 0. Now this 40 kilonewton, okay, this distributed load will create a moment. Okay, so this load is equal to 320. Okay, if we convert this into a point load, this 320 can be converted into a point load, and it will act at a distance of 4 meters from the point A. Plus we have another load, that is the reaction at B, that is this is equal to By. What we have in the FBD further is this 20 kilonewton and this moment of 150 kilonewton meter. So this UDL will create a moment of 320 into 4, that is 320 into 4, but that will be in the clockwise sense. Therefore, let's take this direction to be negative. Plus By will create an anti-clockwise moment about A. Therefore, we consider it to be a positive moment. So this will act at a distance of 8. Another moment will be created by this 20 kilonewton force. Okay, it will have a force arm of 8 plus 3, that is 11. And it is again going to create a clockwise moment about A. Therefore, treating it to be negative. And finally, we have a couple moment of 150 kilonewton meter, and it is acting in the clockwise direction. Therefore, this will also be taken as negative. So these are all the moments which are acting about point A, that is about the hinge of the beam. So their summation has to be equal to 0. So from here we can get that By will be equal to 206.25 newtons. In fact, kilonewtons. So this is the first reaction, that is the reaction at the support B. So we can substitute this in the first equation and we will get that AY is equal to 340 minus 206.25, and this reaction will be equal to 133.75. So we have calculated both reactions at support A and support B. Now we are going to proceed for the shear force calculations. So we are going to calculate the shear forces at different sections of the beam. So for the first portion, okay, let's calculate the shear force between the section A and B. Okay, so for this we take randomly a section at some distance from A. Suppose this is section 1 of the beam. Let the distance of this section from the support A is equal to x1. And we have a reaction here which is equal to AY, and another reaction here is equal to BY. So how we have defined the shear force in the previous classes, the shear force at section 1 will be equal to summation of all the transverse forces, either from the left hand side of the section or from the right hand side of the section. Suppose we are taking the left hand side of the section. We have to see what is the summation of all the vertical forces with the proper signs, okay, up to section 1. So towards the left of the section, you can see that there is a reaction AY and there will be a UDL, okay, whose magnitude will be equal to 40 into x1, because we are considering only that portion of the beam which is towards the left of 1. Therefore, towards the left of the section 1, we have what? The load is equal to 40 into x1. Therefore, we can see that shear force calculations at section 1 will be equal to this AY. Since we are taking the left hand side of the section, therefore the upward forces have to be taken as positive as per the sign convention. So there, this will be AY. This UDL of 40 into x1, okay, will be negative because it is towards the downwards, okay, it is downwards from the left hand side. Okay, all the loads which are upwards when we are taking the left hand side of the section, they have to be taken as positive, while as the downward loads have to be taken as negative when we are treating the left hand side of the section. So this gives us the relation between the shear force, and this will help us to calculate the shear force between all the points between A and B. So for calculating shear force at A, x1 has to be substituted 0. This will be equal to AY, that will be equal to the reaction which we had calculated, that is equal to 133.75 kilonewton. And to calculate the shear force just to the left of B, I write it as B minus, that is just to the left of B. I will substitute that x1 is equal to 8, therefore it will be equal to 40 into AY minus 40 into 8, that is 133.75 minus 320, and this will be equal to minus 186.25. Okay, so this shear force is actually just to the left of B. Now what will happen exactly at B? There will be, the shear force will be equal to minus 186.25. You can see that at B, suddenly the shear force will get changed due to this reaction in the upward direction, and this has to be taken as positive. Because we are moving from left to right, therefore the upward forces will be taken as positive, while as the downward forces will be taken as negative. So At the point B, there will be a sudden change in the shear force due to this point load, that is due to this reaction. So shear force at B will be equal to minus 186.25 plus we had seen that this reaction is equal to 206.25. So this will be equal to 20 kilonewton. Okay. So this shear force will remain constant up to point C because there isn't any load acting up to point C. Okay. So shear force just to the left of C, that is shear force just to the left of C will also be equal to 20 kilonewton. Okay. That is just to the left of C. And what will happen to the shear force at C? Because there is a point load which is acting in the vertically downward direction. Therefore, there will be a sudden change in the shear force at the point C that will be equal to up to point C. What we have is 20 kilonewton, and this 20 kilonewton is acting in the downward direction. Since we are moving from left to right, therefore the downward force has to be taken as negative. So we will get zero shear force at C. Okay. So now we are in the position to draw the shear force diagram for this loading. We take this, we draw these vertical lines, and we take this reference axis, that is from here we plot the x, and from this direction we plot the shear force. So what will be the shear force at A? You can see that there is a sudden change in the shear force at A due to this reaction. Okay, the shear force at A is equal to 133.75. So this is 133.75. Okay, this will be the shear force at A. Now we can see that what is the shear force at B. So you can see that the shear force just to the left of B will be minus 186.25. Okay, it will be minus 186.25 just to the left of B. So let me take this to be 186.25. Okay, it is just to the left of B, and this will be connected by a straight line because we have seen that whenever we have a uniformly distributed load, the shear force will be a linear function. Okay, it is clear from this equation. Okay, you can see that the shear force varies in the section 1,1, that is between A and B. The variation of the shear force is given by this equation. Okay, ay minus 40x1, which is a linear equation, and it is having a negative slope. Okay, you can see that it will be having a negative slope. Okay, so therefore it will be connected by a line which is having a negative slope. This line is having a negative slope, so this portion will be positive and this will be negative. Okay, so it's clear from this equation that the variation of the shear force between A and B is linear. Okay, and the linear variation is such that it is having a negative slope because x1 is having a minus coefficient here. So this 186.25, okay, negative minus 186.25 is the shear force just to the left of B. So what will happen at B? The shear force at B will be equal to 20 Newton because there is a sudden change in shear force due to this reaction B. Okay, so at B, here there will be a sudden rise in the shear force on the account of this point load, and it will remain constant up to C, and then it falls to 0. So this is the shear force diagram for this loading. Okay, so one important point here is that we can see that there is a point. Okay, let's name it as D. D is a point of zero shear force. Okay, so we can see that this is a point of zero shear force. So now let's go for the bending moment calculations. Okay, so for calculating the bending moment, let's take again a section 1 1, which is at a distance of x1 from the support A. Okay, so if we want to calculate the bending moment at section 1 1, then the bending moment at section 1 1 is equal to the summation of all the moments with proper sign convention, either from the left hand side of the section or from the right hand side of the section. Now let's take this left hand side of the section. Okay, so we can see that the moments will be created by this vertical reaction, that is ay. Okay, ay will create a moment at section 1 1, plus this moment will also be created by this udl. Okay, you can see that this is a udl. This will also create some moment about section 1 1. And as per the sign conventions, if the moment from the left hand side of the section is in the clockwise direction, then it has to be treated as positive. And if it is in the anti-clockwise direction, okay, from the left hand side of the section, if it is in the anti-clockwise direction, then it has to be taken as negative. So you can see that ay will create a clockwise moment about section AA, or section 1 1 in fact. Okay, it will create a clockwise moment. Therefore the moment due to this ay will be treated as positive. At the section A, section 1 1 is at a distance of x1 from this load A1, AY. Okay, so this moment will be positive. Now about this UDL, okay, this UDL is having a magnitude of, this UDL is having a magnitude of 40 into x1, okay, because we are taking only this portion of the beam which is having a span of x1. And this UDL will create a moment about 1 1 in the anti-clockwise direction. Therefore, all the moments which are in the anti-clockwise direction from the left-hand side of the section, okay, from the left-hand side of the section, they have to be taken as negative. Therefore, this will be equal to 40x1. This will be the load, okay? And we know that since it is a UDL, therefore, this load will be acting, this load will be assumed to act, this load will be acting at the centroid, that is, it will be acting at a distance of x1 by 2. Therefore, this is the load and this is the force arm. So this moment at the section 1 1, it will be equal to ay is equal to 133.75 x1 minus 20 x1 square. So to calculate the moment at A, bending moment at A, we substitute x1 is equal to 0, and we will get that bending moment at A is equal to 0. Also to calculate the bending moment at B, we substitute x1 is equal to 8. That is, it will be equal to 133.75 minus 133.75 multiplied by 8, and this will be equal to, so what we have seen that if we are going to plot the bending moment with respect to the x, at x equal to 0, we have seen that bending moment is equal to 0. And at x equal to 8, that is at the point B, bending moment is equal to minus 210. Therefore, this bending moment will be below the reference x-axis, okay? It is a negative bending moment. But see here, we can't predict the variation of this bending moment in this span, okay? One thing clear to us is that the bending moment in the section 1 1, that is bending moment between the points A and B, will be parabolic in nature, because bending moment is a function of x1 square, that is, it is a parabolic function. The variation of the bending moment will be parabola, okay? But we can't say that what curve is going to connect, whether we are going to get this kind of a parabola or we are getting this directly, this parabola, okay? So we can't predict the behavior of the this bending moment curve between A and B. But there is one important point to note, that there is a relation that which we are going to see in the upcoming lectures. It's a very important relation, that shear force at any point is equal to the slope of the bending moment curve at that point. Okay, so this is one important relation, that shear force at any point. I'm going to derive this relation in the upcoming lectures, that shear force at any point is equal to the rate of change of bending, the change of bending moment with respect to x, that is v is equal to dm by dx. So we can see that there is a point where there is a zero shear force. You can see that there is a point D where we have zero shear force. Okay, so if this shear force is zero at any point, then what can we say about that is bending moment is maximum. Bending moment will be maximum at that point, because the differentiation of the maximum quantity, okay, if the bending moment is a function of x, and uh, if we differentiate it and its differential comes out to be zero, then we can say that the bending moment at that point is maximum. So one important thing to remember is that bending moment is maximum when shear force is zero, or shear force change sign. We can see that at this point the shear force is zero, and therefore this point will be the point at which the bending moment will be maximum. So before connecting the curve, the bending moment curve between A and B, it's important to calculate the maximum value of the bending moment. Okay, on that basis we are going to predict the variation of the bending moment curve. Okay, we are going to draw the bending moment curve properly. So let's find the location of the zero shear force. You can see that the location of the zero shear force will be given by this equation, by equating this to be zero. So we can see that shear force at section 1 was equal to ay minus 40x1. So if this is equal to 0, then we get that x1 is equal to ay by 40, and this will come out to be and this is equal to 3.34 meters, which means that this distance is equal to, okay, this distance will be equal to 3.34 meters. That is, at this location the shear force is 0 and the bending moment will be maximum. Okay, the bending moment will be maximum. One more thing is that how can we find the location of the maximum bending moment? We could also have differentiated this bending moment. Okay, so we can see that this bending moment is equal to bending moment at section 1 it is equal to 133.75 x1 minus 20 x1 square. So if I am differentiating this bending moment with respect to x, this will be equal to 133.75 minus 40 x1. So this has to be 0. Okay, for the maxima or minima, this has to be 0. So from here we get that x1 is equal to 133.75 divided by 40. So this is also equal to 3.34. That is, at this location, the bending moment will be maximum. Now, how can we say that it is for the maximum? We can take the second derivative, because this can be the condition of maxima or minima. The second derivative will be 0 minus 40. That is, it will be equal to minus 40. Since this comes out to be negative, This is negative, therefore this is the condition of maxima. Therefore, at x1 is equal to 3.34 meters, the bending moment will be maximum. So I want to calculate the maximum value of the bending moment. Therefore, I will put in this bending moment equation, x1 is equal to 3.34 because that will be the location of the maximum bending moment. Therefore, this maximum value of the bending moment comes out to be 224 kilonewton meter. Okay, so this is the maximum value of the bending moment. So we can see that this point here will be the point of maximum bending moment. And the magnitude of the maximum bending moment will be equal to 224 kilonewton meter. Okay, so we have seen that the bending moment at A is equal to 0, at B it is equal to minus 210, but at some point or at some distance of, that is 3.34 meters from the support A, the bending moment will be equal to 224 kilonewton. Now we know that this there is a parabola which is going to connect them. We have two types of parabola. One is having the increasing slope and another is having the decreasing slope. But we can see the relation, see this relation, P is equal to dm by dx. Okay, the slope of this parabola is depending upon the shear force. Okay, the slope of this parabola is going to depend upon the shear force because the bending moment curve is a parabola. Therefore, the slope of the parabola, that is the slope of the bending moment curve, will depend upon the shear force. So let's see what is the variation of the shear force between this point A to the point of maximum bending moment or zero shear force. In this case, see here, if this is the point D, I can take this to be the point D. This is point A, and this is point B. This will be point C. From A to D, we can see that shear force is decreasing. Okay, the shear force is decreasing. Therefore, the slope of the parabola should also decrease because the slope of the parabola or the slope of the bending moment is depending upon the shear force. Okay, it is equal to the shear force. Therefore, since shear force is decreasing from A to D, you can clearly see that shear force is maximum, and that is having 133.75, and it is having a value of 0 here. Okay, so from A to D, shear force is decreasing. Therefore, the slope of the parabola should also decrease. Therefore, this is the parabola which is going to connect them. Because see here, it is having a decreasing slope. The tangent drawn at this point will be having a greater slope. And as we go on moving upwards, the slope of the tangent is going to decrease. Okay, the slope of the tangent is going to decrease. So see here, there are actually two types of parabola which you can connect them. This is of the decreasing slope, and this parabola is of the increasing slope, this blue color. Okay, so see here in the first case, if I draw the tangent, it has higher slope. Now the slope of the tangent is decreasing, therefore the slope is going to decrease. But see, in this parabola, initially the slope is lower, but now the slope is going to increase. Okay, but my variation of the slope will depend upon the shear force, and from A to D the shear force is decreasing, therefore the slope should decrease, and the tangent here, the tangents which I want to draw are, their slopes is decreasing. Okay, the slope of the tangents is decreasing. Finally, what is going to connect 224, that is the point D of the bending moment curve with the point B of the bending moment curve. Again, it will be depending upon what? It will be depending upon the shear force. See here, the slope of the bending moment curve is equal to shear force. Okay, now see in this region, the shear force is increasing. Okay, the shear force is increasing, although the magnitude is negative, or although it is negative, but the magnitude is increasing. Therefore, from D to B, the shear force is increasing. Okay, we can see that the shear force is increasing from D to B. Therefore, the slope of the parabola, which is going to connect it, bending moment at D with the bending moment at B, should increase. Okay, the slope should increase. Therefore, in this case, the parabola will be somewhere like this. Okay, I can just correct it, but it is clear that its slope is going to increase. Because see, the shear force, the slope is depending on the shear force. Okay, the slope is equal to the shear force. Now the shear force is decreasing, sorry, increasing. Okay, it is increasing from D to B. Okay, this is the point B. Therefore, the slope is going to increase. Again, you can see that if I draw the tangent here, the tangent will have less slope, but as I am going towards the point B, the slope of the tangent is going to increase. Okay, so this is the variation of the bending moment. Again, you can see that from A to D, the shear force was positive. From A to D, the shear force is positive. From D to B, shear force is negative. Therefore, the slope from A to B should be positive. Therefore, if I draw a tangent here, this is a tangent. This tangent is having a positive slope. Okay, you can see that this line, it is a positive slope line. Okay, this line is having a positive slope line. But see the tangents which are drawn from D to B. Okay, if I draw a tangent from D to B, I will get this tangent. That is, I'm getting this tangent. This is having negative slope, and this tangent is having a positive slope. Obviously, the shear force here is negative. You can see that the shear force in this region is negative. Therefore, the slope of the bending moment curve will be negative. But from A to D, the shear force was positive. Therefore, the slope was positive. Okay, it's clear from this equation. Now we are left with the task of calculating the shear force at the bending moment at B and C. Okay, although we have calculated it at B, now we are going to calculate it at C. For that, we have to take another section at a distance of x2. Okay, so for calculating the bending moment between A and B, we had taken a section in this region. Now to calculate the bending moment at C, we can take a section between B and C. Okay, so this section will be at a distance of x2. Now this 40 kilonewton intensity, okay, UTL load can be broken into a point load whose magnitude will be equal to 320, and its distance from this section will be equal to x2 minus 4. See here, this distance is x2, this distance will be 4, therefore this distance will be x2 minus 4. And you can also see that we have a reaction here. This reaction will be acting at a distance of x2 minus 8. Okay, if I want to calculate the moment due to the shear this reaction, it will have a force arm of x2 minus 8. Okay, now let's calculate the bending moment at section 2. From the left hand side of the section, the reaction AY will create a positive bending moment because it will be clockwise. Therefore, AY into x2, this 320 will create a negative bending moment because from the left hand side of the section, the bending moment will be anti-clockwise. Okay, about this section, the bending moment created by this 320 will be in the anti-clockwise direction. Therefore, 320 into x2 minus 4. Okay, and this by will create a clockwise movement about this section 2. Therefore, it has to be treated as positive as per the sign conventions of the bending moment because we are taking the left hand side of the section. Okay, so this will be again positive, that is by into x2 minus 8. Okay, so we can put the respective values. AY is equal to this will be 320 into 4, that will be equal to By is equal to 206.25. Okay, so this will give us the variation of the bending moment, and we can see that this gets simplified to minus 370 plus 2x2. In fact, we will have a x2 here, by into x2, therefore 206.25 into x2 minus 8 by, that will be equal to 8 into by is equal to 206.25. And this equation will get simplified to minus 370 plus 2x2. So this will give us the bending moment at any section between B and C. Okay, so at x2 is equal to 8, we will get bending moment at B. So this will be equal to minus 370 plus 2 into x2 here is equal to 8. Sorry, not 2x2, here it will be 20x2, just correct it. So this will be equal to minus 370 plus 160. So this will be equal to minus 210. Okay, this is equal to minus 210. It is the same bending moment which we had seen in the previous case as well. Okay, it is bending moment at B, it is equal to minus 210. Now bending moment at C, for that we have to put x2 is equal to 11. It will be equal to minus 370 plus 20 into 11, that is, this will be equal to minus 370 plus, that will be equal to minus 150. Okay, so this is the bending moment actually just to the left of C. This minus 150, it is just to the left of C, and the variation will be linear. You can see that this bending moment equation is having a linear relation. Okay, you can see that m22 varies linearly with x2, therefore it will be a straight line. And what will happen here is that at C there is a clockwise moment of 150 as well. Okay, this is minus 150 at a clockwise moment of 150 just to the right of C. If I take a section, then I will have a clockwise movement, and clockwise from the left hand side of the section will be positive. Therefore, the shear force, this bending moment curve will end at 0 here. Okay, it will end at 0. So this is the positive bending moment, and this is the negative bending moment. Okay. So actually what is here, this minus 150 is just to the left of C. And at C, there is a sudden change in bending moment due to a couple. of 150, okay, due to a couple of 150 Newton, due to a couple of 150 kilonewton meter. Let's discuss one more question. You can see that this is a simply supported beam having a hinge at A and a roller at B. The hinge reactions will be AY, that is in the vertically upward direction. Actually, the hinge reactions are two reactions, horizontal reaction, but since we are dealing only with the transverse loads, therefore the hinge reaction in the horizontal direction will be 0. While as in the roller support, at the roller support, we will have only the vertical reaction. So this AY plus BY, as per the equilibrium of the beam, should be equal to the net load, that is equal to the area under the loading diagram. Since this is a distributed load, therefore half of base into height. This will be equal to 27 kilonewton. Now, to calculate the moment about any hinge or any point, we can consider the beam. This is the beam. And we know that for the calculation of the moments, we have to convert this point, this UDL or UVL into the point load, okay? Whether it is a UDL or a UVL, for the moment calculations, we need to convert it into a point load so that we can get a definite force arm. Now this load we have seen, it is having a magnitude of 27 kilonewton, and this acts at the centroid of the loading diagram. Therefore, since this is equal to 9 meters, therefore this distance will be equal to 3 meters, and this distance will be equal to 6 meters. Okay, we know it from the concept of the centroid that it is located at the distance of L by 3 from the maximum intensity. Okay, 2 by 3 to L by 3 from the zero intensity, and at a distance of L by 3 from the maximum intensity. Okay, so this is A, this is B, and the reactions were AY and BY. So summation of the moments about A should be equal to 0. Now this 27 will create a clockwise moment about A. Let's take it to be negative. 27 into 6 minus this is creating an anti-clockwise moment about A. Therefore, it will be taken as positive. So 9 BY, this has to be equal to 0. So we get that BY is equal to 27 into 6 divided by 9. So this will be equal to 18 kilonewton. The reaction at the support will be equal to 18 kilonewton, and this will be equal to 9. Okay, AY will be equal to 27 minus 18, that is equal to 9 kilonewton. So we can start drawing the shear force diagram first by considering a section between A and B. If this is A, this is B, we have seen that this reaction is equal to 9 and this reaction is equal to 18. Let's take a section at a distance of 1, section 1, 1 at a distance of x. So the shear force at this section will be equal to the summation of all the transverse loads either from the left hand side or from the right hand side of the section. So if we are taking the left hand side of the section, the transverse loads which we are having is equal to it is equal to AY, and this uniformly varying load, okay, this uniformly varying load, look at here at this section, the intensity is not 6. Okay, the intensity of the load is 6 at this extreme end, okay, at the extreme end at the roller support. But if I am considering a section, okay, you can see that this intensity will be less than 6. Okay, it will be less than 6. Therefore, what is actually the condition here is that this is 6 and I want to calculate the intensity at this distance, okay, because I have taken section at a distance of x. This total is equal to 9, okay. So I want to find the loading intensity here, okay. Let this loading intensity be equal to omega dash, okay. So from the similar triangle concept, you can see that the bigger triangle is in similar with the smaller triangle. Therefore, 6 by 9 will be equal to, okay, 6 by 9 will be equal to omega by x, which implies that omega will be equal to 2 by 3x, okay. So this is the loading intensity at this section, okay. This is the loading intensity at this section. So omega is equal to 2 by 3x, okay. This is the height of the small triangle which I will get here. Therefore, the height of this small triangle will be equal to 2 by 3x, and the width or the base of this triangle is equal to x. So this gives me the area of the loading diagram between A and the section 1, 1. Okay, this is a small triangle whose base is equal to x, and this loading intensity, that is the height we have calculated, it is equal to 2 by 3x. So shear force will be equal to, at this section, ay minus x square by 3. Okay, so we can see that shear force at A, then I have to take x equal to 0, which implies shear force at A will be equal to ay. That is, shear force at A is equal to ay, that is equal to 9 kilonewton. Also, the shear force at B, for that I have to take x is equal to 9, that will be equal to 9 minus 9 square by 3. That will be equal to 9 minus 27. This will be equal to minus 18. That is, shear force at B is equal to minus 18. Okay. So we can see that the shear force at A is equal to 9 and shear force at B is equal to minus 18. And also look at the variation of the shear force. The shear force variation is proportional to, this gives us that the shear force variation is proportional to x square. That is, we are going to get a quadratic curve here, or a parabolic curve of the shear force. Okay, we had seen that if there is a UDL between 2 points, the shear force will be a straight line and the bending moment will have parabolic behavior. But whenever there is a UVL, the shear force will have the parabolic behavior and the bending moment will have a cubic behavior. Okay, bending moment will be a function of x cube, that we will see later on. So this gives us the variation of the shear force. Okay, so if we are going to draw the shear force diagram, one thing we can note that the shear force here is equal to 9 and the shear force here is equal to minus 18. Therefore, definitely there will be, if this curve is to be connected, there will be a point of zero shear force. Okay, there will be a point of zero shear force. Now we want to find the location of the zero shear force. Therefore, for finding the location of zero shear force, that is, V at 1, 1 should be equal to 0, which means that ay minus x square by 3 should be equal to 0. Which means that x square should be equal to, that is, it should be equal to 3 into the value of ay was 9, that is, x will be equal to plus minus under root of 27. Obviously we will skip the negative value. Therefore, we will take only the positive value, that is under root of 27. That will be equal to, this comes out to be 5.2. So what actually here gives us location of zero shear force? And this will also be the location of the maximum bending moment. Okay, so let's make bending moment calculations first. So for bending moment calculations at the section 1.1, we can see that the bending moment at any section is equal to the summation of all the moments created by the transverse loads, either from the left hand side or from the right hand side. Now, if we are going to consider the left hand side of the section, the bending moment due to this AY will be in the clockwise direction about section 1.1. Therefore, this has to be treated as positive. That is sagging bending moment. Okay. So AY into X, and this transverse load in the downward direction, that is this UVL, is going to create a anti-clockwise moment about section 1.1, and from the left hand side of the section, the anti-clockwise moments, bending moments, are taken to be negative. Therefore, it will be equal to minus, the load is equal to 1/2, base was X, the height of this triangle was 2/3X, and this moment arm will be equal to, see here, this this UEL, okay, for the small triangle can act at a distance of, it will act at a distance of x/3. This will act at a distance of x/3. So if this is 2/3x, then this load will act at a distance of x/3, because it will act at the centroid of this small right angular triangle. So here we can see that the bending moment at section 1.1 will be equal to AYX minus 2 and 2 will cancel. We will get that x cubed by 9. Okay. So this is the variation of the bending moment in this region, that is from A to B. Obviously, we had predicted that it will be a cubic curve. You can see that the bending moment variation is cubic. Okay. So obviously we will get that moment at A, we can put x to be 0, which gives us moment at A is equal to 0. And if we want to find the moment at B, then we have to put the value of x to be 9. Then it will be equal to the reaction AY is equal to 9 multiplied by this x is equal to 9 minus x is equal to 9, that is 9 cubed divided by 9. Therefore, we will get 9 square minus 9 square, that will be equal to 0. So bending moment at A and B is equal to 0. But we are interested in finding the maximum value of the bending moment. So the maximum value of the bending moment will be, for that we have to put x is equal to 5.2 meters, because this is location of zero shear force. So the bending moment equation is equal to AYX minus x cube by 9 substituting AY is equal to 9 and x is equal to 5.2, that is at this location the bending moment will be maximum. Solving this, it comes out to be 31.17 kilonewton meter, or we can take it to be 31.2 kilonewton meter. So this is the maximum value of the bending moment. Now we can draw the SFD and BMD. Okay, as it is a solid problem on the book, we can see that this will be the shear force and bending moment diagrams. Okay, so we had seen that the shear force at A is equal to 9 and the shear force at B is equal to minus 18. And there was a point where we had a zero shear force and it is located at a distance of 5.2 meters from this support A. We had taken this to be A and this to be B. Also see here, from A to this point, let's treat this point to be C. Okay, the point where we have zero shear force. C is a point of zero shear force. Now we know that the variation of the shear force was parabolic. That is, variation of shear force was function of x square. Okay, it's mentioned here 9 minus x square by 3. But what kind of parabola should we draw? There is a relation between the distributed load and the shear. Okay, this relation I'm going to derive in the next lecture. So omega is equal to dv by dx. Okay, this is the intensity of the load. Okay, it's the intensity of the distributed load. See here the intensity of the distributed load, and since this, if this distributed load is acting in the upward direction, then we have to take it to be positive. But in our case, this distributed load is acting in the negative direction, therefore minus omega dv by dx. Okay, if omega is negative, that is, it is acting in the downward direction. So from this relation, we can see that the slope, okay, in our case, it is this omega is in the downward direction, therefore it has to be treated as negative. Therefore, our slope of the shear force curve is negative. Okay. Also, you can see that the intensity of the load is increasing. Okay, from A to C. Okay, if this is the point C, intensity of the load is increasing. Therefore, the slope of the shear force curve should increase. You can see that initially there is less slope. As we go on from A to C, the slope is increasing. Okay, as we go on from A to C, the slope is increasing because it is clearly mentioned from this equation that the slope is equal to the intensity of the loading. If the intensity of the loading is not constant, here the intensity of the loading is not constant, it is varying, therefore, and the intensity of the loading is increased. Okay, it is increasing from 0 to the maximum value at 6. Therefore, the slope of the shear force curve will go on increasing. Therefore, initially we have less slope, and as we go on from A to C, the slope is increasing. Similarly, from C to B, the intensity is increasing. Okay, the intensity is increasing. Therefore, the slope is again increasing. Okay, the slope is again increasing. Therefore, when we are moving from C to B, that is from 0 shear force to minus 18, you can see that the tangent, if we draw the tangents, the slope will go on increasing. We also saw the BMD calculations. It was 0 here. It was 0 at this end as well. And the maximum value was 31.2. Okay. And this is the cubic curve which is connecting them. Okay. This is the cubic curve which is connecting them. Again, the behavior of this cubic curve will depend upon the shear force diagram. See, the shear force is decreasing from A to C. Okay. From A to C, it is decreasing from 9 to 0. Therefore, the slope should decrease. Okay, the slope should be decreasing. And similarly, the slope will go on increasing because the shear force is increasing from C to B. Therefore, from C to B, the bending moment slope will go on increasing. Okay.